The third thing I want to talk about as a hobbyist building a motor, just to get something working, is, and particularly this applies to permanent magnet DC motors or any type of motor where you need a commutator, any type of DC motor basically, and that is commutation. Now, we need to commutate the machine because we have our field here like this with that, and we can set a coil up inside this that will come in here and like that, and we pass a current through our coil and we get a magnetic field like that. And when that rotates, that will reach a steady state position here and here, where its north is attracted to there and its south is attracted to there. And we need to commutate it in order to remove this and put the north back up here and the south down here, in which case this north will be repelled from this north and this south will be attracted to there to continue our rotation. We'll talk more about that later. What I want to talk about now is the actual mechanics of building your own commutator. So most students or most builders will build something a little bit like this, where we have our coil, our permanent magnets, and then they will bring each end of it out and put it onto something like this. This is a copper bracket that's used in plumbing that they've cut the lugs off and glued on here, and this is quite a common thing to do, and it works quite well actually. Now, if we are trying to get a reasonable current into here, and we want to do it without sparking, the way that a lot of students will do it is you can basically put some wires on here, like this. And that kind of works. How they do that, there's a couple of ways of doing it. Here's an example that has been done over here. And here is our commutator. This one has been built out of copper tape. The coils have been terminated onto the commutator, and then as it spins we can see that the power which comes in through this copper wire here contacts there, and as it goes around it will be the break and reconnect in the other one to do with what I talked about here. Now, the idea of using one wire, and as I said it does work, it's not optimal by any stretch of the imagination. And the reason it's not particularly optimal is because if we consider our copper strip or our bracket, whichever one of these ones we're looking at, whether it be this one or this one here, if we look at it from the top, we see here it is here with our piece of wire going across it. If we look at it from the end, here it is here with our piece of wire going across it, and at a sort of 45-degree quartering away aspect we might see something like this, and with a mirror on this side of course, and we've got our wire running across it here. Now, with a single wire we only have one point of contact, and that's it there. I can show that with two curved surfaces with my trusty highlighters. If we've got the shaft here and our brush here, there is only a very small point of contact there. Okay, that is going to be a high resistance junction. It's not going to pass much current, and as it goes over these points here, there's going to be a lot of sparking. So having a single wire, as I said, it does work, but it's not optimal. A better idea is some way of increasing this surface area. And if you're dealing with a smooth surface like this, the easiest and the best way to increase the surface area is to not use a single wire, but to maybe use a strip of something, like this. And that way our contact area goes from this single wire here to this entire area here. And this is what this one here is, I've done. This one here is actually quite good because it shows both. We've got our shaft here, and they've got one of these brackets they've used here to obtain a large point of contact. And on the other one they've got one wire. So this one here shows both. It shows that large long line of contact and the single point of contact, which I showed with the highlighters before. If we go back to that, sorry, this here, this single wire, as I said, is analogous to this, with that one single point of contact. This side here is like that, and we now have that entire length of contact. We're going to get a far greater current transfer across this mechanical junction here with that than we were that. The next thing to do would be to make it send it out in another direction, and that would be to maybe something like this one here, where they've used multiple wires to create it. But you want to get away, if you want a machine that's going to work well and work efficiently and get maximum power transfer and deliver as much current as you want or as you can get through, you want to get away from this and move into this. Some people who have built them, as I said, we saw that bracket. Others have used actually paper clips and various other things like that to obtain this larger surface contact area around the commutation. The second aspect of commutation that some students or some people who build their motors do wrong is they energize the coils in the wrong point. You want your machine to be energized with that. You do, when your coil, and I'm going to pretend we've got a core on it here. That is what you do not want. You do not want it energized in that condition, because that is not going to rotate. That is not what we want. We want it to be energized we don't want it to be energized in that condition. Okay? We want it to be energized when it's in that condition there. Because it's when it's in this condition here, this north and this north are going to repel. This north and this south are going to attract. This south and this south are going to repel. This south and this north are going to attract. We will get rotation like that. So we want it to be energized when it's in this condition, not this condition and not this condition. To do that, you need to make sure that your machine is going to be energized when these are in the right place. Okay? There's a big difference between here and here, and that can easily be adjusted by whether you connect here or here. Okay? We can connect here and then they're energized. We can connect here and they're energized. But in this condition, that's disconnected. Thank you for watching.